Okay. The next one is multiple optima. And actually, let me give you a concrete example. Let us consider a linear programming problem subject to inequality constraints, and we have also non-negativeness constraints here. And let us solve this problem using the standard simplex method. So what do we need to do first is to convert inequalities to equalities by adding slack variables to the left-hand side of the inequality constraint. So that's what we do first. So here we are adding x3, x4. That allows us to convert inequalities to equalities, and we have to say that the slack variables are non-negative. Now, let us solve the problem using the simplex method, meaning first comes the simplex tableau. So we know that the first row would come actually from the first equality constraint, so we would just write down the leading coefficients in front of each optimization variable. And here we would have the right-hand side of the constraints, the same for the second constraint, and the final row comes from the cost function. Okay. So let us perform the pivoting operation. So which of the variables will be the pivoting variable? Which of them has the largest influence on the cost function? x1, because it has the smallest negative or largest negative value. Okay, so that would be our pivoting variable. Okay, and now we will increase value of x1. Which constraint will be violated first? The first one or the second one? Okay, so the ratio here is 2 and the ratio here is 3. Okay, 4 over 2 is 2, 3 over 1 is 3. And actually we are looking for the smallest positive value of the ratio. So it's the first constraint. Okay. So we are now going to perform elementary row operations such that we obtain 1 here, 0 there, and 0 there as well. Okay. So when we want to do that, we actually have to subtract the 1/2 of the first row from the second row. Okay. So we will do that. We obtain this row. Now, how can we obtain 0 here is by adding 1/2 of the first row to the final one. Okay. So that's what we do. And to actually convert the 2 entry here to 1, we need to divide the whole row by 2. Okay. So we have obtained this simplex tableau. And now we can perform classification of the solution. So first of all, is this an optimal solution? So for that we have to look at the coefficients in the final row. If all of them are positive, then we know that we have found the optimal solution. Okay, so here the solution is optimal because all coefficients are positive. And now, what is actually the solution? Okay, so we know that the simplex tableau actually allows us to classify the variables in 2 groups. The first one are so-called free variables. So the free variables are those which are not basic variables. So basic variable has this one entry in the whole column. All other entries are 0. So the other variables are free variables, and we set them to 0. The basic variables are equal to the right-hand side of the constraint. So x1 would be 2, x4 would be 1. Okay? And that's actually our optimal solution. So the optimal solution of this problem is x1 equal to 2, x2 equal to 0. That's the optimal solution, and the value of the objective function is 2. Okay? So by performing a single pivot operation, we have found the optimal solution. Okay? But let us consider that for any reason, for instance, by modifying the heuristics, we would choose this variable as the pivoting variable. So we also need to identify the corresponding pivoting column. So which of them would it be? Would it be the first one or the second one? Again, we have to look at the ratios between, well, 4 over 1 is the first ratio, and 3 divided by 2 is the second ratio, and we are looking for the smallest positive value, so it's the second one, which is the smallest. Okay? So here, now the objective is to get 1 here, 0 there, 0 there, by elementary row operations. So we will do that. And we obtain this solution. Is this solution optimal? No, because one of the entries in the final row is still negative. Okay? So we have to pivot further. Okay? So we choose this variable as the pivoting one. Now we only have one choice. We have no other choice but the first variable. So again, which of these two constraints will be violated first? Well, 2.5 divided by 1.5 and 1.5 divided by 0.5. Clearly, this ratio here is smaller, so that would be the pivoting row, and we perform the same pivoting operation as before. And we obtain this simplex tableau. Is this an optimal solution? It is, because all entries are non-negative. And we again perform the classification. And actually what you might see is that we have the same value of the objective function as before. But actually the solution is different. Before it was, I believe, what was it? 2, 0 was the optimal solution. So x1 was 2 and x2 was 0. Now we have a different solution. x1 is 5/3 and x2 is 2/3. So we have two solutions which are different but are equally good. Okay? So these are the optimal solutions. They are very different, but they are actually of the same quality. And what happened here is that if we draw the constraints of this optimization problem, that's why I have bothered you so much by drawing the constraints. So clearly, these two constraints are just x1 non-negative and x2 non-negative. Okay? And then this, in the original formulation, this was 2x1 plus x2 smaller than 4, and here it was x1 plus 2x2 smaller than 3. Okay? So we have these two constraints. Now, the optimal solution, one of them, this 2, 0, is here, and the other one is there. So what has really happened here and why this multiplicity of the solution has occurred is that look at the objective function. If I would ask you to draw that objective function, how would it look like? So we can take, so we are drawing this one, so let's take x1 as 0. Okay? So x2 would be 1. Okay. If we take x1 to 0.5, then x2 would be 0. Okay. So actually the objective function looks like this, and we are maximizing it, so we are moving it to the right. And actually what happens here is that the objective function is parallel to this constraint here. It's actually this constraint, x1 plus 2x2 smaller than 3. Okay. So just look here and compare this line with this one. Okay. No, it's this one. Okay. So just multiply this line by 2, and we will obtain exactly this constraint. Okay. So it says that the objective function was parallel to the constraint which is active at the optimum, and that's exactly the situation where multiplicity of optima occurs. If we have the problem posed in such a way that the objective function is parallel to the optimal active constraint. So that's what it said here. Actually, all points that we find, regardless of which pivoting variable we choose, all these optimal solutions are identically good. However, and especially when we obtain optimization in control, when we solve optimal control problems as linear programming problems, that multiplicity of the optima is highly undesirable in practice. And the reason is the following. Multiplicity essentially means that you change your state measurement slightly and you obtain maybe a different choice of the control action, which is equally good as for some other algorithm. Essentially, it means that even though you don't change your measurements, your optimal control action can start switching between two or maybe even between multiple values. Okay? So the problem there is that despite your system is not doing anything, your optimization algorithm returns different control actions. And that obviously is not good for the physics of the system, because changing the control action always induces stress on the actuators. So obviously, if the measurements don't change, we would also like the control action to stay constant. However, if we formulate optimal control problems as linear programming problems, what can happen is that despite of the measurements being fixed, the control action changes constantly. And that's not good for the physical operation of the system. So therefore, we have to be aware of this fact and accommodate for it accordingly. Yeah?
Even if you use the same algorithm? Because the thing seems like it is that always with the same thing.
Yeah, the problem is that those modern optimization algorithms, they usually apply some, I would call them, tricks inside. And some of those tricks are based on randomization, which means that if you run the same algorithm with the same input data twice, you might end up in different vertices. So essentially what we are saying is if we go...
So like choosing the randomly.
Yeah, something like that. It's not really choosing the... where do I have that example? I was looking for the graph again. Probably I messed up. Ah, it's here. Okay. Ah, right here. Okay. So essentially, then the small random perturbations can cause that the solver once converges here and the other time it converges there. Okay. So that is actually a big problem in optimal control when using linear programming. So linear programming can be applied to to solve optimal control problems, but we have to be aware that this problem can occur. So essentially, then you have to do something on top of the optimization algorithm. Essentially, you have to record the optimal solution from the previous sampling instant along with the cost function. And then when you obtain a solution which has the same value of the cost function, you just use the solution from the previous time instant. Okay? Well, provided the input to the algorithm didn't change, of course, because if the algorithm, if the input is new, obviously also the solution might change. Okay? So just remember that to avoid multiple optima, well, we cannot really avoid that. We just can build something on top of the existing algorithm to kind of reject the multiplicity.